We are diving deep today into a piece of research that really challenges how we think about scaling large language models.
It's a fantastic one.
The paper is Dynamic Large Concept Models, Latent Reasoning in an Adaptive Semantic Space, and it's from researchers at ByteDance, the University of Manchester, and a few others. So if you're looking for the big takeaway, it's this. The fundamental problem with current LLMs is that they apply the same amount of computation to every single token.
Exactly. It doesn't matter if it's a simple the or a critical keyword.
And this paper just argues that's a massive waste of resources.
It is a massive waste. I mean, think about language itself. It's not uniform at all. You have these, boilerplate phrases, predictable words,
Right.
where compute is just functionally wasted. But then you hit a really sharp, semantically important transition, a new idea, and the model often doesn't have enough capacity allocated right there.
And that's where the Dynamic Large Concept Model, or DLCM, comes in. It's a hierarchical framework that basically learns where those semantic boundaries are on its own.
It does. It learns them from the latent representations and then compresses tokens into this higher level concept space.
And that's where the real thinking happens.
That's where the deep reasoning is performed. It shifts the computation away from processing every single redundant token and puts it into a much higher capacity concept backbone. And the results are pretty compelling.
What are the numbers?
At a compression setting of 4:1, so 4 tokens per concept, they reallocated about a third of the inference compute and got an average improvement of plus 2.69% across 12 zero-shot benchmarks.
And that's all while matching the baseline model's total inference FLOPs.
Exactly. This isn't just about getting bigger, it's about scaling smarter.
Scaling smarter. I love that. So let's unpack this. Why is this token uniform approach such a conceptual failure?
Well, the paper makes a really good case that reasoning itself is hierarchical. But a standard autoregressive model doesn't have any explicit way to abstract things.
It just predicts the next word.
It just predicts the next word over and over. So it's forced to kind of reinfer the main idea of a paragraph again and again implicitly. DLCM says, no, let's create an intermediate level of granularity. Let's create a concept.
And this isn't a fixed thing, like a sentence.
No, and that's the key. It's not a single token, and it's not a human-defined sentence. It's a variable length chunk of meaning that the model learns from the data, end to end.
That learned variable length part is what really sets it apart from previous attempts, right? We've seen latent reasoning models before.
We have, but they tend to be black boxes. They work in this continuous hidden space, but you lose interpretability.
And then there were the large concept models, LCMs.
Right, and those had the opposite problem. They reasoned on concepts, but the concepts were rigid, usually whole sentences or fixed-size blocks of text.
Which I imagine creates a huge engineering headache.
A scalability nightmare. You had to pre-train these massive separate encoders and decoders. It just wasn't practical, and the model couldn't adapt its chunking size to the content. DLCM avoids all of that.
Okay, so let's walk through the architecture. The paper lays out a 4-stage pipeline. How does it go from raw tokens to these reasoned concepts and then back to a prediction?
Absolutely. So think of it as a processing hierarchy. Stage 1 is just encoding. A lightweight encoder takes the input tokens and turns them into your standard fine-grained representations. Nothing too new there.
Stage 2, though. This is where the magic starts. Dynamic segmentation.
Correct. This is the new component. It learns where the semantic breaks are, and then it pools the tokens inside those boundaries into a single compressed concept representation.
And this step dramatically shortens the sequence. So if you have a sequence of length L, the new concept sequence is, 4 times shorter?
Precisely, for R equals 4, and that leads to stage 3. Concept-level reasoning, this is the heavyweight component. A really big, high-capacity transformer, the concept backbone, does all its reasoning only on that short, compressed sequence.
So all that compute that would have been spread thin across every token is now concentrated right here.
That's the idea. And finally, you have to get back to predicting a token. So stage 4 is token-level decoding.
Right.
A decoder takes the reasoned concepts and reconstructs the token-level predictions using causal cross-attention. The tokens look back at the fully reasoned concepts.
That separation seems so elegant. But that dynamic segmentation part must be incredibly tricky. How does the model even figure out where a semantic break is without supervision?
The intuition behind it is actually pretty simple. They hypothesize that a semantic transition corresponds to a big shift in the hidden feature space.
Between, say, token T-1 and token T.
Exactly. They just measure the local dissimilarity. They project the token reps into a query and a key space and calculate the cosine dissimilarity. If the two tokens are very different, boom, that's likely the start of a new concept.
Okay, that makes sense. But I can see a problem right away. What about different types of text? A dense academic paper versus, a simple story? The information density is completely different.
And they hit that exact problem. Just using local boundaries meant it was impossible to maintain a target compression ratio. The model would just overcompress the easy stuff.
And that's where this global load balancing mechanism comes in.
Yes, the auxiliary loss, LO. It's a critical engineering constraint. They needed the model to be able to adapt its chunking locally, but they also needed the average compression rate across the whole batch to hit their target.
So the local segmentation is deciding the size of each data packet, but this global parser is like a traffic regulator for the whole network, making sure the overall flow is right.
Perfect analogy. It enforces the constraint globally across the entire distributed batch. And the ablation study on this was so telling.
What did it show?
Without that global regularization, just trying to enforce it per sequence, the actual compression ratio they got was only about 3.15. The model was just undercompressing everything.
And with the global constraint.
They hit 3.92, almost dead on their target of 4. It just shows that for these kinds of novel architectures, managing the global training stability is just as important as the local mechanism itself.
That theme of stability keeps coming up. It's there again when they talk about training this heterogeneous architecture using decoupled maximal update parametrization, or VLP. Why wasn't standard T good enough here?
Standard P just assumes your model is, uniform, that every layer is roughly the same width. DLCM completely breaks that. You have these tiny token-level components and then this massive concept backbone.
So their widths, D-token and D-concept, are totally different.
Wildly different. And if you try to train them with the same learning rate scaling, the whole thing becomes unstable, especially when you try to scale the model up or down.
So they had to decouple it. How does that work? How do you balance the learning between a giant component and two small ones?
They scaled the learning rates for each component independently. The core finding was that the optimal learning rate for each part scales inversely with its own specific width.
So bigger component, smaller learning rate. Smaller component, or relatively higher learning rate.
Precisely. It balances the updates, so the big concept brain doesn't just overwhelm the smaller token handlers. It's a key engineering trick that makes the whole thing stable and trainable.
Okay, so beyond just the stability, they also grounded this in theory by extending the scaling laws we're all familiar with. We usually just talk about parameters N and data, D.
Right. They introduced a compression-aware scaling law that adds 2 more factors: the compression ratio, R, and the percentage of parameters allocated to the concept backbone, P.
Why is that so important?
Because it lets you make principled decisions. Under a fixed FLOP's budget, it tells you the best way to design your model. Should you compress more and make the backbone even bigger? This law gives you the answer.
And they found the theory actually held up in practice.
It did. The framework generalized well, and their predicted compute multiplier of about 1.4 was right in line with established baselines like Chinchilla. The theory is solid.
Which brings us to why they chose R equals 4. I mean, you could theoretically compress even more and save more FLOPs.
You could, but R equals 4 was the sweet spot. It was the best balance they found between training stability, efficiency, and what you might call intuitive semantic segmentation. Go too high, and you start merging ideas that shouldn't be merged.
So even though the total parameter count of DLCM is higher, 2.3 billion versus 1.3 billion for the baseline, the effective FLOPs are the same because of that compression.
Exactly. They prove their goal. Redistribute capacity for better efficiency. Don't just add more parameters blindly.
Okay, so we have the theory, we have stable training. But there's one more engineering hurdle we need to talk about before we get to the results. That's the decoding stage.
Yes. The cross-attention bottleneck.
The tokens need to attend to the concepts. But since the concepts are variable length, you end up with this really irregular attention mask.
It's a memory access nightmare. Standard GPU kernels, they just hate irregular memory patterns. Using something like flex attention was just too slow.
So they came up with this concept replication strategy. What is that?
It's a really clever and simple solution, actually. It's analogous to grouped query attention. They just take the short concept sequence, the keys and values, and expand it.
Wait, They just copy the concepts?
They just copy them using repeat interleave. So for every token that belongs to concept A, they copy concept A's representation. For every token in concept B, they copy concept B.
And that transforms the messy, irregular L by M mask into a standard, hardware-friendly L by L causal mask.
Exactly, which means they can use the super optimized flash attention Varlin kernels.
And the speedup was significant.
It was huge. It ranged from about 1.26x to 1.73x faster than FEX attention. And the key thing is the advantage got bigger as the sequence length increased.
Really?
Yeah, it peaked at that 1.73x speedup for 16,000 token sequences. That proves the bottleneck wasn't the computation, it was the chaotic memory access patterns from the dynamic mask.
All right. A theoretically sound, stably trained, efficiently implemented system. Let's get to the proof, the results. The average gain was plus 2.69%, but where did it really shine?
The gains really show the architectural bias. It did consistently better on tasks that need high-level, multi-step reasoning. Things like OpenBook QA saw a jump of plus 3.00%. ARC Easy was up 2.61%.
Common sense reasoning.
Exactly. It confirms that pushing all that capacity into the concept backbone really did optimize the model for deeper reasoning.
But every design choice is a trade-off. If you're focusing on the big picture, you must be losing some of the fine detail. Where did it do worse?
You're right. They saw some mild regressions on tasks that are really sensitive to token-level details. BoolQ, for example, dropped by about 1.47%. RACI was down 0.72%.
Hold on. A drop of nearly 1.5% on BoolQ. That's a fact-checking, precision-critical task. Doesn't that make this approach a non-starter for things like enterprise RR or high-precision code completion?
That's a completely fair challenge, and it gets to the heart of the trade-off. DLCM is explicitly choosing global coherence over local precision. For tasks like abstractive summarization or long-form Q&A, that's a great trade. For something where a single token being wrong is a failure, maybe not.
So it's about choosing the right tool for the job.
It's an explicit capacity management decision. You sacrifice a tiny bit of precision inside the concepts to gain a much better understanding of the boundaries between the concepts.
Now, they visualize that trade-off perfectly with that U-shaped loss analysis. Can you describe that?
Yeah, this was a great experiment. They looked at the prediction error based on a token's relative position within a concept chunk, and they found this distinct U-shape. Meaning the model got way better, those are the green bars in the chart, at the very beginning and very end of concepts. It was nailing the transitions.
So it's like a copy editor who focuses all their energy on the first and last sentence of every paragraph.
That's a perfect way to put it. In the middle of the concept, performance was mixed, sometimes even a little worse than the baseline. It's literally focusing its power on understanding the start and end of a semantic unit.
Proving the architecture is doing exactly what they designed it to do.
Exactly.
And finally, they proved the adaptive part was working too, with the content adaptive compression analysis.
Right. They confirmed it's not just making uniform chunks. When they fed it different kinds of text, it compressed them differently. Technical English, for example, was kept in longer chunks, about 10 tokens per concept.
But something more structured.
Light code was compressed into much tighter units, only about 6 tokens per concept.
So it's adapting the granularity to the content's density.
It is. It's successfully respecting that global compression budget while maximizing information retention based on the material itself.
This has been a fascinating look at architectural efficiency. I think the synthesis is pretty clear. DLCM shows that it's not just about how much compute you have, but where you put it.
Absolutely. Shifting that budget from uniform token processing to a compressed concept backbone is just as important as scaling up model size or data. It's a huge win for efficiency.
It really feels like the era of just uniform processing might be coming to a close.
It could be.
The discovery of these learned, variable-length concepts that just emerge on their own from the data, it leaves a really important question for all of you to think about. What other high-level linguistic units could models learn and use for reasoning if we just stopped forcing them to process everything one token at a time? Maybe the future of language modeling isn't words at all.